Hey everybody, this is Larry. This is me going with Q3 of the Bi-Weekly Contest 161 Network Recovery Pathways. Hit the like button, subscribe button, join me on Discord, let me know what you think about this one. I think the only tricky part about this one, for me anyway, is to understand the problem. I spent a long time trying to understand what it is asking for. I mean, of course, there you have words like that, you have a lot of words, and then just try to figure out what it's asking for. And I think the way that, for me, may not be for everybody, right, necessarily, the way that opened my eyes was just thinking that, okay, there's almost an infinite amount of paths. All we need to find is one path in which the minimum edge is the maximum. So I still struggle a little bit to even explain it. But all you would need to do is find one path, or the highest path, right, where this is the case. And you don't have to return the actual path, you just have to return the existence of a path, right? If there exists a path in which the minimum edge cost, or the edge cost, or the score is this edge, the target, then so if you have a routed path in which you can calculate the score, then then that means that it exists, right? And it almost kind of reminds me of those like decision problems of like that's kind of used in NP problems. This is not an NP problem, but kind of like that along those lines, of like, okay, well, if this exists, then like you only get one, you get a query on whether it exists or not. And it is a very hard to understand for me, and as a result, to explain what they meant, right? But once you understood it, once I took a while to understood it, just means that if there any path at all, where 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 the score, which means the minimum edge of a path, is some target, then you're good. And for me, the way that I kind of think about it is that, okay, well, if we calculate the shortest path with one get us to figure out whether a path exists, right? So shortest path means that whether a path exists for, but the problem with a shortest path is that it will give us, if we do a shortest path on the top recovery, or the total recovery cost, so that it stays under K, it will probably also give us something that does not give us the maximum, like like for example, or even say this one, right? Like in the purest of the ways, if you go the shortest path will only go from 0, 2, and 3, and just ignore the left side. But you also know that oh, I mean, I think in this case the cost is 15 and 15 is greater than 10, but let's pretend that K is 0 to infinity for now, right? The two paths at the node 3, the shortest path is going to be 7. You're going to not have this one, right? The idea here is that, okay, let's say we remove all edges smaller than 3 and 4, or in this case, let's say we want to test for 5, right? We want to test for 5, we remove all the edges smaller than 5. And the reason because of that is that, well, if you don't use any edges that are less than 5, then they cannot be the minimum edge cost along that path, right? And because they're not, then the minimum edge cost along that any paths at all is going to be 5, right? Because that's your target, and you eliminate anything after that, even if 5's not on here, right? And that's basically the idea. And then I check, now that we have this graph where we remove all those things, and the online thing also took me a little bit, online offline also took me a long time to maybe not a long time, but still some time to understand, because it's just like you could just not have that node in the input, so it's just very confusing to me. I don't know. I mean, it's just like an if statement, so I don't, like, I guess someone could make a mistake and forgot about it, but very silly. But in any case, yeah, you don't need to know all the paths, but knowing that one path exists where these constraints are met, that's all you need. And that's basically it. Yeah. So for that, you just do a binary search, right? You see if does a path exist in which the score is X, and then if it does, then we just try something higher, right? And that's basically the way that I have here, right? Binary search, I'm not going. Oh, I did get a wrong answer because I forgot the -1 case for not possible. It's pretty straightforward. If 0 is not good, meaning that the entire graph is in there and it doesn't, you could also write it that way, I suppose. Then you just return -1. But otherwise, yeah. So this is binary search. I'm not going to go over binary search for this problem. It is a hard problem. Maybe it's a little bit of an easier hard problem, but I think you should just know binary search. And there are more other videos for it, so I'm not going to go over in this video because I don't want to spend too much time on it. But on this function, I think, yeah, this is just the shortest path, Dijkstra's algorithm, right? Nothing too fancy. I'm not going to go over this in too much detail except for how we define the implicit edges. Because you have the edges that are given to you by the input, but then there's this part where target is the smallest edge on the graph, right? So that means that, okay, if the node that you're traveling has to be online, if the edge has to be greater than you go to target, and yeah, and then the rest is Dijkstra kind of. This part is Dijkstra, right? So if you make an improvement on the path, and then this part is just the constraint that you have to hold to, which is the cost one. I think, where is it? The total recovery cost does not exceed K, right? So you have to kind of just, I put it here, right? And then you go there. If you're able to reach the last node, then I return true, meaning that there is a path that satisfies all those conditions for all the edges. Otherwise, we return false, and then we just do a binary search. What is the complexity here, right? Max for me is just 10 to the 9. We could do something about max edge weight, but this is a little bit easier for me. And also, this only means about 30 iterations, right? 2 to the 30. So yeah, so 30 iterations, and then this is of course all of all of v log y, right? So it's gonna be v log y times log range, which for this problem is fast enough because we don't have that many edges. Keep in mind that nodes are actually 5 times 10 to the 4th. Edges goes to 10 to the 5th at most, which is not that. And we won't. This is the part we're logging on, and this is the part that's n, right? Or n or v or whatever. So let me write it out real quick. So this is going to be O of v log y. This is O of log r for range. So total, it is going to be O of v or log r times log or v log e, right? And that's it. That's all I have for this one. Let me know what you think. I'm going to focus here on the good function. This is the binary search, and this is just the top for setting up. And that's it. That's all I have for this one. Let me know what you think. Thanks for watching. And you can watch me doing the contest now. Down one in a while, that's why. Hopefully I didn't make a silly mistake. Okay. I haven't done it. I usually do it, I don't know, any other way. Maybe with a breadth first search. Maybe I should have done it with a breadth first search. Either way. Alright, Q3, and there's a Q4. So far so good. Alright, let's go. Async, we have a DAG, 0 to n-1, UV cost. Okay, some nodes online, 0 and online, the total what's the recovery cost? They talk about, oh, the recovery cost is the cost. All intermediate nodes, okay, that's not, okay. You find the total recovery cost is less than K, the amount of cost of the minimum edge, its score is the minimum edge cost along that path. Return, what the, man, there's so many layers. Return the max path score, the largest minimum edge score, okay. The recovery cost of all edges, the total recovery cost is the minimum edge cost. Okay. Return the maximum. There's so many minimum, maximum things that are so hard to read. Return the maximum path score amount of valid paths. What does it be offline and online? Or how do you turn it online? I don't get it. What is online and offline? Like, it doesn't say anything. It just say that this is online. So do we just ignore nodes that are offline? I'm so confused. If that's the case, then why do we care about offline nodes? Okay. So yeah, so why do we care about offline nodes? This is so confusing. I thought recovery means like turn it on. It's just like a totally useless information, which is kind of really weird. But okay, fine. Let's see. 0, 1, 3, 5, 10, 15. So this path is invalid. Okay. Min cost. Okay, total cost is 7. The min edge cost is 3. The maximum of all valid paths. I mean, this sounds like just like a regular BFS problem, but it's just so hard to read for some reason. The min edge cost along this path. What if there are multiple paths? Okay, so if there are multiple paths, what does that mean? Online is really weird, but okay, fine. Okay, so on each node we want to store so of all the edges, this is such a weird one. Okay, so this part is just shortest path, right? But along that shortest path, you also, it's not just shortest path, it is all possible paths, right? But this is a DAG, so okay, so that's the key part, is that this is a DAG, and because this is a DAG, there's a dynamic programming solution maybe. K is pretty big though, so maybe not. And the cost is pretty big, so maybe not. What is K again? K is the total cost cap. I mean, it still feels like it's, I don't know how there cannot, I mean, there could be like a, there be at most 10 to the 5th edges, that's fine. The largest min edge cost. Is this a binary search problem? I mean, I guess it feels intuitive with all the min-max thing, because then now you do a BFS on the min, on the binary search, right? Because now you do a binary search to see whether it is possible. Is that true? It sounds roughly right. Edge is 10 to the 9, so okay. Okay, if this is possible, we have to try bigger. So that means our left is equal to mid. Okay, and then now what's good? good means that there exists a path largest min edge. Okay, yeah, so that means that amongst all valid paths though, is that right? Because that means that you have to consider all the edges. And this is so hard to read or understand. Because you can't just eliminate the small edges, right? Because they still create valid paths, it's just that it doesn't. I don't get it. I don't know if this is just a gotcha where there's no optimization and it's just always true. Because it's just about getting all valid paths. And you can't turn on anything, so I don't get it. Am I just confusing this problem? Are they just kind of confusing you? And is it BFS? Can you do BFS? So minimum. Okay, so I mean it's almost like we want the shortest path by the minimum path, but we want to make sure that there is a path in which it reaches, right? So how do we assure that? You assure it by you just construct it backwards. Does it even matter backwards or forwards? I feel like that's a gotcha. Maybe that's not binary search. Well, let's just keep here of it. Because the minimum doesn't change. Oh wait, this is the largest minimum. So wait, that's not quite right. The largest minimum. What does the largest minimum mean? But I don't think there is a binary search. Largest minimum means that is there a path? Okay, maybe there is. It's just asking, is there a path that goes through? Okay, maybe it is binary search, because then now the formulation is that you don't take any edges smaller than it and still be able to get in. Okay, yeah, that's right. I think I had this idea in my head, but I just okay, yeah, and I just kind of got confusing along the way. But yeah, okay, fine. Okay, so yeah, okay, what are we doing? It's just so hard to read. I think that's all. Also, this is not a deck. Why do I keep saying it's buffer search? It's clearly dice driven. Okay, right. What is N? Did they tell you N? What is N? N is equal to online.length. Okay, that makes sense actually. I forgot for some reason. Because online.length is useless. I don't know why it is there. It just makes things complicated. Okay, yeah. That's what I forgot. This looked a little awkward. distance. And then for VC G sub node, if on line of V and C is greater than equal to target, then because we just have to find the existence of a path. So okay, yeah, that's why. Okay, and now if this is true, then well, n best sub V is greater than best of node plus C. Okay. Oops, nope. V. It could probably also terminate, but yeah. I guess this is actually return false. We want to write something like if node is equal to n-1 and return true because there is a path there. Okay, I forgot. It has to be bigger than 9, that's why. 5, 6. Whew, why do I think it's 5? 5 doesn't even make sense. 5 goes 0 to 1, 1 to 3. Oh, I forgot the K thing. Okay. Yeah, okay. So this is not true. This is well, this is the first time. So if D is greater than K, then return false, right? I think technically I want something like this instead, but also n best of node plus C is less than equal to K. Maybe that's a little bit cleaner. I always have to remember. Okay. It's my medication timer thing. I always forget though. YOLO. Oh, empty cases. I forgot about the -1 actually altogether. Like I don't return. There's no way for me to return -1. So I was thinking about that actually, but then I just forgot because I got distracted because this problem is so confusing. But yeah, silly mistake. Because we could have done it, but I should have left a note for myself because I was like, oh, remember to think about -1 later. But then I saw that everything is good. I just forgot. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy to your mental health. I'll see y'all later and take care. Bye bye.